So I wanted to go over drawing Lewis structures in a slightly different way than the way I presented in class, which was the NASL method. It's similar to what you saw in another video that I posted, and it doesn't involve as much calculation. The only calculation you need to do is adding up the valence electrons of the atoms in your molecule. And from there, it's a matter of making bonds, filling in the lone pairs, and then sometimes you take lone pairs to make double or triple bonds as needed. So I'm hoping that this will simplify it for you a little bit. Not so much focus on the numbers, but just more of the process. So I'm going to show you the steps, and then I'm going to go through a few examples that have some of the different things that you might encounter. Okay, so first of all, here are the steps. Some of this is similar to what we've already done. First step is always place your atoms, right? Place the least electronegative or farthest from fluorine in the middle, or if it's carbon, you can always put it in the middle. Never put hydrogen in the middle. All those same rules still apply. Then you go around the molecule and add up all the valence electrons. So again, this is the only time you need to work with the numbers. You're not doing the needs available, all that stuff. It's just the available, really. Count up the valence electrons of each atom in the molecule, add them together. Then start by placing a bond between the central atom and however many terminal atoms there are. Use any remaining atoms, keep in mind that that takes 2 atoms per bond. Use any remaining electrons to fill the octets starting around the outside. And if the central atom doesn't have a full octet at the end of that process, then you need to take some of those outer atoms and move them in to create double or triple bonds as needed until the center atom is full. So again, it's coming at it from just a slightly different perspective. It gets you to the same result. Involves a little bit less working with the numbers and more just figuring out how many you've got to work with and working with them until everybody is satisfied. So let's take a look at some examples. The most important part for this process, and really for the NASL if you do that too, is understanding the connection between the periodic table and the valence electrons. Remember that the group numbers, 1 valence electron, 2 valence electrons, 3, 4, 5, 6, 7, 8. Now, in these problems, we're talking about covalent bonds. We're really going to live in the 4 to 7 range. Okay, the 8s, the noble gases, don't tend to form bonds. The 1, 2s, and 3s, those are your metallic elements that are going to tend to form ions. So really, we're in this area of the periodic table almost exclusively. So let's take a look. Silicon, first of all, place your atoms, right? Place your atoms in an arrangement that makes sense. The least electronegative, which is the furthest from fluorine. Obviously, silicon is farther from fluorine than fluorine is from itself. So we put silicon in the middle and put those others around it. Now let's look at the valence electrons. Silicon is down here in group 14. So it has 4. And then fluorine is here at the top of group 7. So it has 7. But because of the 4 here, you either multiply it by 4 or you can add it 4 times, however you want to do it. But the end result is going to be the same. We're going to have 32 electrons total in this molecule. 4 from the silicon and 7 each from 4 different fluorines. Now, start by placing a bond between the center atom and each of the outside atoms. Again, this is where it's a little different from the NASL method. We're going to start just making bonds. That used up 8 of my electrons because it takes 2 to make a bond. And you'll even see some examples of Lewis structures where they don't even draw the lines. They actually just put dots in here to show that they're shared between them. I like to draw the lines because, it's a bond. It's a connection between the 2 atoms. And I think the line gives you more of the feeling of that. But you always have to remember that each line represents 2 electrons. So that's why I draw the dots on the ends. Okay, so we've used 8 electrons, which means now we have 24 electrons left. So let's move to the outside atoms. Fluorine has 2 electrons connected to it, which means it needs 6 more. Each fluorine needs 6 more electrons to fill its octet. Okay, well, now count it up. Each fluorine has 6 dots, that's 24 dots, and then each bond is 2 electrons times 4, that's 8. So I've used all 32 electrons. They're all there. Now, I know the fluorines are full because I used all those dots to fill them up. The silicon in the middle has 4 bonds, that's 8 electrons. I'm done. Okay, every atom in the molecule has a full octet. I've used all the electrons that I started with from the valence electrons and don't have any left over, don't have any extra. That's it, I don't have to do anything else. Let's take a look at another one, NCl3. So N is here, chlorine is here. So it's close, but nitrogen is farther away than chlorine from fluorine. It also makes sense that the nitrogen would be in the middle of these 3 chlorines, but it's not always 100% the case that the one that, it's 1 and 3, that you put the 1 in the middle. But when in doubt, do that and you'll be right. And also keep in mind that it's whichever one's farther away from fluorine should be in the middle. Okay, now, valence electrons. Nitrogen is in group 15, fluorine is in group 17. So 5 for nitrogen plus 7 plus 7 plus 7 for the 3 chlorines. That's 26 total valence electrons. Start by making bonds. Okay, so that's 6. I've got 20 left. Look at the outside atoms. Each chlorine has a bond, which gives it 2. So each chlorine needs 6 more. So 6 plus 6 plus 6, that's 18. Plus the 6 I used to make the bonds, that's 24. I had 26, I've got 2 left. And as it happens, the nitrogen in the middle needs 2 more electrons to complete its outer octet. So each chlorine has 8. The nitrogen now has 8. And I've used all my electrons, so I'm done. Don't need to do anything else. Water. I've seen this a lot. You're going to always see this one a lot. Oxygen, hydrogen, hydrogen. Okay, so oxygen is over here. It has 1. There's 2 of them. Plus oxygen is here. It has 6. So that gives me 8 electrons to work with. Make the bonds. That's 4 electrons. I have 4 left. You don't want to ever put dots on a hydrogen. Hydrogen has 2 electrons by the bond, and that's all it needs. That's all it can hold. Which means now we got to look at the oxygen. It has 4 right now. So if we put 4 dots around it, and I drew it that way because really it looks like this in terms of the shape. Okay, so the oxygen now has 4 electrons from the bonds plus 4 lone pair dots, total of 8. That one's done. Hydrogen has 2 from the bonds. That's done. Okay, HCN. So we've got carbon, we've got nitrogen, we've got hydrogen. And you might say, well, definitely hydrogen is the farthest away, but remember, hydrogen can't ever be in the middle. So other than the hydrogen, the farther one from fluorine is carbon. Compared to, it's a little farther than nitrogen, so carbon's going to go in the middle, hydrogen, nitrogen on the outside. Hydrogen has 1 valence electron, carbon has 4, nitrogen has 5. That gives me a total of 10 valence electrons. All right. If I start with a bond there and a bond there, that's 4. I have 6 more. Well, I can't put any of the dots on the hydrogen. The nitrogen needs 6 more. Okay, great. Now the nitrogen is done, but the carbon is stuck now with only the 2 bonds. It only has 4 electrons attached to it. So this is where you need that last step, where sometimes you need to take the electrons from the valence and move them to create a bond. Okay, so I get rid of them. Well, now carbon has 6. So if I move these, I actually create a triple bond. Now, to clean this up a little bit, hydrogen has 2 with the bond here. Right, that bond is 2 electrons. Carbon has those 2 plus 3 bonds on this side. That's a total of 4 bonds, which makes 8 electrons. Nitrogen has the 3 bonds, which is 6. It still has 2 of those lone pairs over there. That gives it 8. So each atom has a complete octet. And we've used 2 plus 6 is 8, plus 2 more is 10. I used the 10 electrons I started with, and I created extra bonds as needed to complete that center atom. All right, H2CO. All right, so again, hydrogen, carbon, oxygen. Oxygen is close to fluorine. That's not going to be in the middle. Carbon is farther away from fluorine. Hydrogen is farther away, but because hydrogen can't be in the middle, that means carbon is the farthest away that's not hydrogen. So I'm going to put that in the middle. Valence electrons. Hydrogen has 1. The subscript means there's 2 of them. So 1 plus 1, not 1 times 2. Plus the carbon has 4. It's in group 14. Oxygen has 6 because it's in group 16. Add that all up. It gives me 12. Okay. Create the bonds from the center atom to the terminal atoms. That takes 10. That takes 6. And then oxygen can take the other 6 to fill its octet. Okay, so there's 12 electrons. Hydrogen each has a bond. It's done. Oxygen has 8 electrons, 6 dots plus the bond is 8. Carbon, though, only has 6 because it has 3 bonds. We replicate or remedy that by moving 2 of these electrons to create a double bond. Now, 1, 2, 3, 4 bonds are on the carbon. That's 8 electrons. 2 bonds plus 4 dots are on the oxygen. That's 8 electrons. Each hydrogen has 2 from the bonds. So every atom is complete. I used 12 electrons, which is what I started with. So I am done with this one. I needed to use those 2 electrons from the oxygen to create the double bond to finish satisfying the carbon. And last one, CO2, carbon, oxygen. Oxygen, we've seen this one a lot too. This is a very common one. And so we've got carbon and oxygen. Valence electrons, 4 for carbon, plus 6 for the 2 oxygens. That gives me 16. Make the bonds. Okay, that took 4. I've got 12 left. Complete the octets on the outside. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's my 16 electrons total. 4 for the bonds, 12 for the dots. Each oxygen is satisfied because it has 6 dots on a bond. That's 8. Carbon, though, right now only has 4. So it needs 4 more. Again, we fix that by taking lone pair electrons and using them to make additional bonds. Now, this one, You might sort of look at and say, well, I could just move two more from the left to make a triple bond, which you could, but wherever possible, things are going to be symmetrical. So rather than making a triple bond on one side and a single bond on the other, I'm going to make two double bonds, one on either side. So I used a pair of electrons from each of the oxygens to create a double bond on either side. 1, 2, 2, 3, 4. That's 8 electrons around the carbon. 2 bonds plus 4 dots. That's 8 around the oxygen, and the same on the other side. Okay, so again, that's just a different method. If the NaSl method makes sense to you, use it. If this makes more sense to you, use it. This is slightly different from the way it was presented in the other video. So again, whichever one of these three techniques makes the most sense is the one that you should use. Now, I didn't do the shapes or the polarities on these, but this would be a linear because it has 2 bond regions and no lone pairs on the center atom. And as far as polarity, it has the same terminal atoms on both sides, so that doesn't decide it. And there are no lone pairs on the center atom, so that means if the terminal atoms are the same and there are no lone pairs, it's nonpolar. Okay, this one, it has 3 bond regions or 3 electron regions, no lone pairs. They're all bond regions. That makes this shape trigonal planar. Again, fancy term for a flat triangle. As far as polarity, first question, are all the terminal atoms the same? No, they're not. There's 2 hydrogens and an oxygen. You can stop right there. The terminal atoms aren't the same, it's polar. And move on. Okay, here we have a carbon that has 2 regions of bonds. Right? One side has the hydrogen, the other side has the nitrogen. So the triple bond, remember, it only counts as one region of electrons. How many atoms is the central atom connected to? 2. So there are 2 bond regions. No lone pairs on the center atom. That makes the shape linear. Are the terminal atoms the same? Nope. 2 different terminal atoms. Polar. If you can't answer yes to that first question, are they all the same? It's polar. You don't even have to ask the second question. Water. It has 4 electron regions, 2 bonds, and 2 lone pairs. That makes the shape something called bent. Okay, it's not a straight line. Now, are the terminal atoms the same? Yes, they're both hydrogen. Okay, that doesn't answer it. Second question, does the center atom have lone pairs? Yes, polar. Okay, so if you answer no to the first question, it's polar. If you answer yes to the second question, it's polar. Okay, so you kind of just have to keep that in mind. Moving back, NCl3. Made the circles make this a little harder to see, but just to recreate it here really quickly. I'm not going to put all the lone pairs on the outer atoms because they don't affect the shape or the polarity. So there are 4 regions here, a lone pair and 3 bonds. That's called trigonal pyramidal. So it's a triangular pyramid as opposed to a trigonal planar, which is a flat triangle. This is a pyramid with a triangle base. All right, first question for polarity. Are the terminal atoms all the same? Yes, they're all chlorine. Second question, are there lone pairs on the center atom? Yes, there are. It's polar. All right, I think we're back to our first molecule, which was the SiF4, silicon tetrafluoride. It has 4 regions around it. All four are bonds with no lone pairs. That's called a tetrahedral. And so the questions, are the terminal atoms all the same? Yes. Next question, are there any lone pairs on the center atom? No. If all the terminal atoms are the same and there are no lone pairs, it's nonpolar. Okay, so that's how you figure out those shapes and polarity. And again, that's another method for doing the Lewis structure to begin with. So I hope that helps.